be studying regarding measurement and signal processing. Till now we have studied a lot of analysis, how to find dynamic system natural frequency, its force response, and their instability analysis. In any machinery, generally when we design the machinery, when we manufacture it, and when we commission the machine, then because of inherent dynamics inside the machine, it is having vibrations, which is nothing but after effect of whatever is the dynamics going on inside the machine comes out as a vibration and noise. Measurement of these vibrations is very important, especially in terms of when we are looking into the machinery condition monitoring, and generally we measure vibration in terms of either displacement, velocity, or acceleration, and measurement of the vibration is very important. And if whatever we are measuring, if it's not correct, or whatever the instrument which we are using is not proper, then we may conclude wrong decisions regarding the condition of the machine. Another aspect is there, when we measure the vibration, then we depict those vibration in various forms, so that we can understand what kind of dynamics is going on inside the machinery, which element of the machine is having certain problems. Those problems will be reflected in the measurements. So, when we take the measurement, we should have enough background behind the signal processing, so that we should not make any mistake in measuring them. Also, if we have some research program by which we are trying to understand the condition of the machine, then the theoretical background behind the signal processing is also important, how it works, because there are various equipments which has all the built-in functions by which you can able to measure the response, but you should know how correct they are, and whether you are using them properly. So, first let us see various kind of plots which we will be making it after the measurement. So, there is a spectrum diagram in which we have frequency here, maybe it is in hertz, and here peak amplitude of either velocity or displacements. So, if we take the measurements, the signal may be of this form. Basically, this is the time domain data has been captured, and we have done the fast Fourier transform of the signal. So, it looks like this. Now, another form of the signal is in which we have spin speed here, that is in RPM, which is continuous variation of the let us say a rotor speed, and here we have 1 times the rotational speed magnitude of vibration, maybe velocity or displacement. So, it is having some variation like this. So, here you can see this is corresponding to the critical speed of the shaft. Other form of vibration measurements we can have, like this is a Campbell diagram, in which this axis is spin speed and this is the frequency of the vibration, which is in hertz. Now we have this line which is corresponding to the rotational frequency component, and some more components are there which are twice the rotational frequency, or maybe 3 times the rotational frequency, or even we can have half the rotational frequency components. Now when we are changing the speed of the rotor, we may find there will be corresponding to 1x frequency some amplitudes. As it will reach the critical speed, amplitudes will increase. This circle radius represent the amplitude, and as will go away from the critical speed, it will decrease. Again, maybe if it has second critical speed, we can have amplitudes increasing, and certain faults they give 1/2 the rotational frequency components like this, but in the rest of the locations they will be not there. Similarly, here maybe they can have second x rotational frequency, or some small peaks maybe in the third rotational frequency. Okay. So, this is the Campbell diagram. This particular diagram we have information of the spin speed, also the frequency of excitation, also the amplitude. 3 informations are there. Another kind of diagram which is a 3-dimensional diagram, which is called waterfall diagram. And this is the frequency of the vibration. Spin speed is here in this axis, and magnitude of the vibration is in this direction. So, we can have different speed lines like this, and this is nothing but the something like we measured the time domain signal, and then we did the FFT for a particular speed. So, one particular data will give us a plot like this, in which these are the peaks corresponding to the either first natural frequency or the rotational speed of the rotor. And as we will increase the speed, you may find that these amplitudes may increase or decrease depending upon at which RPM we are rotating the rotor. These also can have various peaks. Okay. So, it is giving some kind of cascade of history of the amplitude as we are changing the speed of the rotor. Now, we will see the measurement and the signal processing. What are the errors involved in that, what precautions we should make during the measurements, and the possible causes of the error and how to avoid them during the measurement. So, first let us see what is the measurement system. So, in measurement system we have a sensor which detect the vibration, this is the detection of the vibration, and it gives in the form of displacement with respect to time. Then we have the interface which converts the analog signal which is measured by the sensor to the digital form, A to T transform. Then we feed this to this signal, the digitized signal, to a personal computer, and there we do the processing of the measured signal. processing and display of the signal. So, this is the measurement system. So, when we measure the analog signal through sensor and transform that to a digital data in the into the computer, then those signals are in the digitized form. So, they will be in the form of numbers. So, let us see how the errors comes in during the digitization of the data. So, let us take a signal which is measured in time domain, is having some this form. This is an analog signal. Now, if we want to digitize it, what we have to do? Let us say we are making a grid. The grid size depends upon the accuracy of the measurement instrument. These are the grids. So, the instrument is having capability to measure the data or digitize the data on these grids. So, these are the this is nothing but the accuracy of the instrument. So, I am just overlapping the grid onto the signal. Okay. Now, when we are digitizing it, so whatever the data are there, they will be at the corner of these grids. So, during digitization, it will take the nearest grid points. So, you can able to see that when I am digitizing the data in the grids, we are not getting the same signal as the actual signal. Signal is all deviating, these red points indicating the data which will be getting after the digitization. So, during digitization of the data, generally the sampling interval we take as constant. So, the sampling interval which we represent as delta t in this figure is given, this is the sampling interval. And once we have digitized the data from analog signal, then we have these data in a form of numbers. N is the number of data, where n is the number of digitized digitized data. During this digitization, we do the digitization of the amplitude, and you can able to see in the figure that we take the nearest node of the analog signal. So, there are some error involved in the sampling of this data, and generally when we transfer this data to computer, we do two basic operations. One is there is signal extraction, and another is the data transformation. So, data transformation is something like when we digitize the data, it is there in the binary form. So, we transform them in a more convenient form, so that we can able to display them in a graphical form. Now, we will see some other kind of problems which we face during the sampling of the signal, and especially when the signal is fast, the frequency of the signal is fast, and if you are sampling that signal with slow, then we may have effect called aliasing effect, in which we will not able to measure the actual signal. So, through one example I would like to explain this phenomena. You must have seen the old movies in which the horse cart wheel, you must have seen that rotating in the opposite direction. Actually it rotates in the same direction, but whatever the sampling frequency of those video frames are there, they are slow at that time. So we could not able to see the wheel of the cart moving in the correct direction. It looks like it is rotating in the opposite direction. So similar effects may occur in the vibration signal if we captured with the slow sampling rate. Through one example I would like to show this. This is a time domain signal xt, and let us say this is the amplitude of that. Let us say this is a perfectly sinusoidal curve. Of same frequency is not changing, amplitude is also not changing. If we sample this particular signal let us say with this period, this is the sampling interval. So second point will be coming somewhere here, third will be coming here, fourth will be coming somewhere here, fifth will be coming somewhere here. So you can see that signal will appear to us like this because of the choice of the sampling interval is different. Actually it is more than the time period of the signal. So this blue color signal will appear as a measurement, but there is something like virtual signal, but actual signal is entirely different. And the theorem behind this is, if let us say we have a signal in which frequency components are less than fc, all the signals which are there in a particular measurement, frequency component is less than fc. If we measure the sample rate is more than 2 fc, then we will be able to measure the signal correctly. It should be more than 2 fc. Like I will give another example in the same signal. Let us say we are having the sampling period as equal to time period by 2 of the signal. Time period of the signal is from here to here. This is the time period of the signal. So if we take the sampling period half of that, so we will be getting, let us say we are starting from here. So these points will be getting as the measurement, and if we join them we will get a signal with 0 mean. So we will not able to see anything in the signal. Okay. So always we should have the sampling interval less than half, so that we can get the correct picture of the signal. This is called aliasing effect. Another example in this, if let us say we have a signal which is having 1 kilohertz, 2 kilohertz and 6 kilohertz signals, and if we are sampling with 10 kilohertz frequency, then we may not get a correct picture of the signal, because 10 hertz is less than twice of the maximum frequency which this signal is containing, that is 2 into 6 is 12 kilohertz. So unless we have sampling frequency more than 12 kilohertz, will not get all these three frequencies correctly. So, if we are using 10 kilohertz as the frequency, we may not able to get the correct picture of this. Instead of this, we may get 4 kilohertz signal. These we will able to measure using the 10 kilohertz, but if we are using 12 kilohertz frequency, then we can able to measure all three components of the frequency, that is 1 kilohertz, 2 kilohertz and 6 kilohertz. In practical situation, when we don't choose the sampling interval arbitrarily, generally what we do, we have some low pass filters. So, we have some frequency below which we allow the signal to pass, because we know what is our requirement of the signals frequencies. Based on our knowledge on the analytical formulations, we will be knowing up to what frequency we are interested in our signal. So, we will be putting a low pass filter for that, and the sampling interval will be decided by then twice of that low pass filter frequency. Now, we will be studying some of the basics regarding the signal processing, like Fourier series, Fourier transform, digital Fourier transform and fast Fourier transform. What is the mathematical background behind that? And because unless we know the mathematical background behind that, whatever during the usage of that, we may misinterpret the signal which we are capturing. So, let us start with the first with the Fourier series. As you know that Fourier series is nothing but when there is a periodic signal, and using Fourier series, that periodic signal can be split into their fundamental harmonic and higher harmonics. That means we can have that particular signal in various harmonic component form. That means the cos and sine terms of the fundamental frequency which that signal is carrying, also their higher harmonics. So, let us see the basic formulas regarding the Fourier series, which you must have studied in the mathematics courses, but our orientation will be toward the signal processing, how these can be utilized. So, first let us see the real Fourier series, in which a particular signal, which is continuous signal, is split into a constant term and summation of various cos and sine terms. Like this, where this omega is nothing but the frequency, where t is the time period of that particular signal, and these constants can be obtained if we multiply this formula by cos n omega t and sin omega t and integrate over the domain. So, it is like this. So, we are multiplying this by cos omega t dt. So, we are getting a n. Similarly, b n can be obtained minus 2 plus t by 2 x t sin n omega t dt. Now, there is another convenient form of the Fourier series is there, that is complex representation of the Fourier series. We have the Euler relation, which can be used to convert the real Fourier series to the complex Fourier series, because complex Fourier series is having some inherent advantage in handling the mathematical terms, is more compact. So, this signal, which is periodic, can be expressed as summation of minus infinity to infinity plus infinity Cn e j omega n t. So, this is the complex representation of the Fourier series, where the complex coefficient now is given like this. Where this n is 0 plus minus 1 plus minus 2 etc. up to infinity, and this particular equation is called complex Fourier series. Complex Fourier series, and this is the complex coefficient of that series, which is related with the real coefficients like this. An and Bn's are the real Fourier series coefficients, and C naught is given by this, and A minus n is given as An plus j Pn by 2. So, from here you can able to see that when we want to have the real part of Cn, that is both in the n when it is positive direction or negative direction, the value of this will be same in either of this direction, because there is, you can see these two terms, real part of that is nothing but An by 2. So, it will be symmetric about the vertical axis. All the components will be symmetric about the vertical axis, and conversely, if you see the imaginary part of Cn, if you want to plot for n is equal to plus and negative, you will find that from first expression this is the negative term minus Bn by 2, but here in the second term is Bn by 2 positive. So, if this term is negative, this will be positive, or if we have this term as positive, it will be negative. So, it will be skew symmetric about the vertical axis. So, here is skew symmetric, but for real case it is symmetric. So, this is some of the characteristic which we would like to keep it in mind. Even the complex Fourier coefficient can be expressed as the magnitude of that and the phase, where the magnitude itself in terms of the real Fourier series coefficients are given like this, and the phase of the Cn is given as tan inverse Bn by An, and and this is, if we plot with respect to if we plot this one, this is called amplitude spectrum, and this theta, this is called phase spectrum. And if we have a plot of Cn modulus square, that is then called power spectrum, which is very common in the Fourier transform. We will be taking one example of a square wave, and we'll obtain the Fourier series of that. So let us see how the signal is. Xt is equal to 1 for a time period, let us say 0 to 1, and for 7 to 8 units, and it is 0 for from 1 to 7, and then it is a periodic, so it repeats after this. So if we want to show this on a picture, it will look like this. This is the time, this is the amplitude, this side. So signal is something like this. So -1, 0, 1, then at 7 it is having amplitude, this amplitude is, let us say, 1, this is 9. So time period of this signal is from here to middle of this, which is 8 units, and this signal repeats after this. So this is a continuous signal in both direction, positive and negative. Now if we want to obtain the Fourier coefficients of this, so let us say complex coefficient C naught, then we have to use the formulae which we have already given previously, where xt is the signal. So this will take the form. Now we are substituting the value of the xt for various regions. So let us say -4, because t is 8, so -4 to -1, that is magnitude of this signal is 0 there, then -1 to 0, or even up to 1 is having magnitude 1. You can see the, so -1 to 1 is having magnitude 1, and prior to that is having 0 magnitude, plus from 1 to 4 again it is having 0 magnitude. Yes. So this will give us, because t is 8, so this will be 2 or 1 by 4, which is nothing but 0.25. Then other coefficients can be obtained like this. So here again from -t by 2 to t by 2 xt dt, and if we start substituting for various period, we will be having -1 to -1, 0 value of this signal, then -1, 0 is having 1 value, but I think here we will be having -j omega n t. Here also we have another term, j omega n t dt. Then from 0 to 1 similar term is there, and for the remaining period again its value is 0. Okay. So if we integrate these two terms and simplify, I am giving the direct solution. This take this form. So Cn is having this value, and if we want to plot these C0 and Cn, we will be getting the spectrum of the signal. The signal will be something like this, in which we have, let us say this is C0 is having some value which is we already obtained earlier, let us say this 2.25. Then this is C1. Similarly, other values will be having C2, C3, 4. This is 4th. Then this is 8, and this is 12. This is 16. So if we obtain the envelope of this, we will get something like this. Sorry, this one is at the bottom. Similarly, this side also will be having this kind of plot. Okay. Now these are the spectrum. These are discrete amplitude, and we have obtained the envelope of that. So it is looking like a smooth curve. And in this particular, this is nothing but spectrum, in which here we have kept the n, and because we know at one particular, any one we can choose, this is nothing but omega, the change in the omega, that itself can be obtained as 1 by t. So basically the horizontal axis represent in some sense the frequency, and the vertical axis represent the amplitude of the spectrum. Now we have already seen the Fourier series. Now let us see the Fourier transform, how it works. Especially in the previous example, we have seen that the square wave, which is periodic in nature, we have done the Fourier series of that, we obtained that. Now if instead of a square periodic signal, let us say we have only a square pulse, and so it is not periodic in nature. So how to obtain the spectrum of that, that will be seen through the Fourier transform. In this case, the basic premise is that once we have let us say square pulse, we assume that pulse that repeats after infinite time. So let us see the signal of that pulse first. So this kind of pulse we have, which is so it's not repeating after after some time interval. So we assume that at t tends to infinity it repeats. That is the assumption. Based on that, we will try to obtain the spectrum of this. So before that, let us go to the expressions of the Fourier transforms, how we can able to do. We have already expression of the Fourier series. In that itself, we are combining that Fourier series and its coefficient in one expression like this. So this is the coefficient which we have substituted in the Fourier series expression. So within the square bracket is the coefficient Cn, and here we have the term of the Fourier series. Now, because we have 2 pi here term, so there will be extra term coming here like this, where this omega is the frequency, t is the time period, the fundamental wave frequency, which we express as like this omega naught, and nth order frequency can be written as omega n. And if we want the difference in the frequency between two order, that is nothing but this, that itself will be omega naught or 2 pi by t. So, because this particular pulse is repeating after infinite time, so if we put the limit, this expression we are putting the limit. So, let us see how it takes the form. X t is equal to minus infinity to infinity 1 by 2 pi. So, this summation terms become in integral minus j omega t. Omega is nothing but n into omega naught term, and 2 pi by t has become delta or d omega. So, basically we have replaced this with omega and delta omega as d omega, and summation with the integral, because once we put the limit t tends to infinity, the period of the signal t is equal to infinity. This expression can be written in more compact form like this. D omega, where this term is expressed as 1 by 2 pi minus infinity to infinity x t e raised to j omega t dt. So, this term is nothing but Fourier transform of the signal x t. This is the Fourier transform of the signal x t, and the previous expression, this expression is called inverse Fourier transform. Fourier transform, which converts the frequency domain signal back to the time domain signal. So, using Fourier transform, we are converting the time domain signal to the frequency domain signal, and using inverse Fourier transform the vice versa. So, let us see with a simple example of a square pulse how the spectrum can be obtained using the Fourier transform, and we will be comparing that spectrum with the Fourier series which we earlier obtained of a square periodic signal, and we will try to correlate them, and that will give us some insight how we can able to do the Fourier spectrum of some other kind of complicated signals. So, the pulse is having this characteristic, is having magnitude 1 for -1 to 1 unit of time, and is having 0 value for all other time. So the Fourier transform of that, as we have defined, will be given as, because most of the time it is having value 0, and during -1 to 1 it is having unit value. So we can retain this term, rest of the terms will be 0. So this gives us, after solving, this is the Fourier transform of the pulse. And if we plot this, let us say this is the pulse this is the pulse, and the whatever the Fourier transform which we obtained, if we plot, we will get a curve something like this, where this is 0, pi, 2 pi, 3 pi and 4 pi, and other side also similar symmetric variation will be there. Now if we want to compare this signal with this spectrum with the previous one, in which we obtain the Fourier series of a square wave. So in that also we got the similar variation of the spectrum. Only thing was we had that in terms of the discrete values, and we obtained the envelope of those spectrum by joining the peaks to get the similar curve as we have obtained using the Fourier transform. So this we have got from the Fourier series of the square wave, that is periodic in nature, and this is the Fourier transform of a square pulse. There is qualitative matching is there between them, but if we want to see the magnitude of this, this is basically Cn, and if we plot this, we multiply this Cn by time period divided by 2 pi, then the magnitude of, let us say, this peak is having 1 by pi value, and this is also having 1 by pi value. That means we have a definite relationship between these two, that is T Cn, which is Fourier series coefficient, divided by 2 pi, is related with the Fourier transform like this. So if we multiply the Fourier series coefficient with time period and divide by 2 pi, we will get the Fourier transform. So now this relation is holding at each and every spectrum. It's not necessary is holding at the peak. You can able to check that it validates at each and every locations, and this particular relation will be using to have spectrum of some kind of signal which is neither a pulse nor they are periodic in nature, but they are finite in length, but they are not periodic. So there is nothing but discrete Fourier transform we call it, because we obtain the frequency domain data from time domain data of a signal which is neither it is periodic, neither it is infinitely long, and that is in between. So, whatever the relation we develop now, we will be using for obtaining the spectrum of a particular signal which generally we measure through the sensors. So, now we already studied the Fourier series and Fourier transform, and we already seen the relationship between them. Fourier series is applicable to a periodic signal, and we can transform that periodic signal from time domain to frequency domain. And in Fourier transform, we have already seen that a pulse which with the assumption that it repeats after infinite time has been converted in the frequency domain, and whatever the characteristic of these two spectrums were there, we related in the previous discussion. Now, the same characteristic we will be using for obtaining the spectrum of a arbitrary signal. Generally, in machinery, when we measure the signal, they will not be periodic in nature, because so many inherent noise effect and so many frequency components are there in the system which we do not know also. They will be there in the system. So, it is very difficult to find out what is the period of the particular signal. So, we take the measurement of that vibration signal for sufficiently long time, and we assume that particular signal contains most of the frequency component of the machine. Now, in Fourier transform, we need a particular signal which is infinite in time, but during measurement this is not practical to measure a signal of infinite time interval. So, in that sense it is finite in whatever the time we measure, that is finite. Also, this is not periodic. So, directly we cannot able to either do the Fourier series of that or Fourier transform of that, but there is a in between. This is called discrete Fourier transform, which utilizes both the Fourier series and Fourier transform relation, which will be using it for this purpose. And the basic premise is that we measure particular signal, and whatever the length of the signal, we assume that is sufficiently long, may not be infinite, and we assume that that signal repeats after next interval. That is the assumption. Based on that, we obtain the Fourier transform of that particular signal, and because that signal is discrete in form, so whatever the spectrum we get is called discrete Fourier transform. In this, when we will be doing the discrete Fourier transform, there are certain errors crept into the signal. As one, we already seen that the aliasing effect. That means, if whatever the frequency components are there in the system, if we are sampling that signal with slow rate, we cannot able to capture them correctly. So, this is one of the aspect. Another is because the length of the signal is finite, and because of that, what will happen, the period of the signal will not coincide with that signal. So, when we do the Fourier transform, we may find that there will be some errors which is called leakage error will occur. So, whatever the frequency components are there in the system, apart from that some more frequency component, there are nothing but leakage error will appear in the spectrum. This is one. Another is another is because we are taking the measurement length of the signal as finite, they are not infinite. So, we will be having problem in that also, some error will be creeping into the spectrum. So, let us see how the sample data is how we do the FFT, the Fourier transform of that. So, for that maybe let us see first the signal itself which we have captured. Signal has been captured in the form of data from x0, x1 up to x minus 1. So, there are total n, capital N number of data are there, and let us say the signal is something like this. This is the signal and this is the time. Now, on this we have obtained, these are the discrete data which we have gathered. Okay. These are the discrete data which we have sampled, and this is x n minus 1, this is x n minus 2. In between some other data are there. Now, the solid line represent the actual signal, but because we have captured up to this as a time period of the signal, we have captured up to x n minus 1 only. So, during when we will be converting this into the frequency domain, for that what we do, this particular signal from x0 to x minus 1 we repeat after the I can use different color from here like this. So, this is representing the x0 and x1 like this, and this is x n minus 1, x n minus 2, and again we repeat the signal like this. This side also we have the repetition of the signal. So, this will represent x n minus 1. So, is similar to that the signal which is there from x0 to x n minus 1 is being cut and pasted at subsequent before and after the signal. So, now we are assuming that this particular signal is having period t, because now as I have shown, now this particular signal repeats after time t, because this is another time period, and with this now we will be doing the Fourier series coefficients we will be obtaining of this particular signal, and then using the analogy between the Fourier series and Fourier transform, we will try to get the discrete Fourier transform coefficient of this particular signal. In the next class also we will continue to explore the DFT, that is the discrete Fourier transform, and fast Fourier transform, because there are some limitation of the discrete Fourier transform. So, how the fast Fourier transform take over that limitations, and then we will see some more detail what are the problems associated with the signal processing. When we do the signal processing, what are the errors involved and how we can